Good evening, everybody. Fun fact, I figured out Respondus last night. It does exactly what it advertises. It records you wanting to take your test, which is creepy. So I did poke around a little bit. Some of y'all need to clean your rooms. One of you ripped a fat vape cloud right before taking the test, which was pretty funny, and you know who you are. So, let's see. What do we have? 30. Nobody cheated though, I don't think. If you did, you were smarter than the system. Okay. Okay. Share. Cool. Okay. So brief recap. Okay. Within the lymphatic system, a functioning part of the lymphatic system is immunity, right? So we talk about like immune boosters and all these other crazy things. The immune system, okay? So the immune system is composed of two different parts. There's innate immunity and adaptive immunity, and barrier immunity, which is different but the same. Barrier immunity, skin, mucus, barriers, physical, actual barriers, right? And then there's innate immunity. And innate immunity is what you're born with. It's a passive type of immunity. Your body naturally produces it. It's almost like a generic version of immunity, right? And then we have specialized version of immunity, which is called adaptive immunity. Adaptive immunity is what builds up over time. Okay, so your innate immunity, always functioning, always learning, always tagging stuff, and just handing it off to the next thing. Your adaptive immunity is building that encyclopedia as you go. Okay, which is why kids are sick all the time, and adults rarely ever get sick. So it's not that you're not exposed to all of that, it's just that your body is better at fighting it off faster. Okay? Also, some immune organs. So lymphoid organs, thyroid, spleen, lymph nodes, as well as parts of the large intestine and the tonsils as well. So palatine tonsils and lingual tonsils as well, kind of. All right, let's go into adaptive immunity. Start. How do I start? From you. Adaptive immunity. All right. So adaptive immunity develops as a result of exposure. So you are exposed to one thing, your body responds, creates a little encyclopedia entry, and then it can recognize it later, right? You pass it later in the hallway and it goes, you, right? So it's a result of exposure. So that's not necessarily to say that you should go exposing yourself to things, but it is to say that things like vaccinations work due to adaptive immunity, right? You give it little tiny amount of a virus that's already dead and it's not going to proliferate. It carries those antigens on the outside of the virus that your body picks up on, and then it goes, "Oh, that's the flu. I've no, I'll keep track of that. And then later, when somebody sneezes in your face at the grocery store, your body goes, hey, I know what that is, and you don't get the flu. Or you get the flu, but it's less severe. Okay, your body heads it off earlier, right? So you, like we were talking about with vaccines, your body heads it off earlier, but it also reduces the response, right? So if it's just growing and growing and growing, and there's a limit that your body catches that. What's happening with adaptive immunity in vaccines is it's lowering that threshold. So it still grows and your body doesn't catch it in time, but it's not building up quite as much. It's not building up exponentially like it would be if your body wasn't exposed to it prior. So all that to say, things like COVID-19 vaccine, that was a big hot topic for a long time. People hate healthcare workers and they think vaccines are poison and all of that. That's not true. And the cell was never to prevent you from getting COVID. It was to catch it earlier and to reduce your symptoms, right? You don't end up in the hospital. That was never the cell. You won't get COVID if you get this vaccine, okay? I don't know if we're talking about vaccines as much in this. I haven't scrolled too far down here, but yeah. So vaccines are good things. They save a lot of people. Go Jan Salk. Okay, so they develop as a result of exposure. They're specific. They're systemic. There's memory. They're versatile, and they tolerate things. So let's talk about specific. Am I going? Hold on. Okay. Specificity. So it's specific to a certain virus. COVID-19, tagged, done, got it. Okay. It's systemic. It creates a systemic response. So it activates other parts of your body and it goes, hey, we're fighting this over here. You should send some friends. All right. There's a memory associated with it. So after it kills all that off, it keeps track of what exactly was attacking your body and it keeps a memory of it. Okay. It's versatile. So COVID-19, SARS-CoV-2, right? What if we have SARS-CoV-1, SARS-CoV-3? Your body can recognize different variations of different coronaviruses, right? So you can fight. That's why the flu works, right? The flu vaccine works, right? So every year, a bunch of really smart doctors get together and they go, what is the flu strain going to be this year based off of what the Southern Hemisphere is doing? What can we expect to see in the Northern Hemisphere? They pick out which strains are the most prevalent. They create a vaccine. You go get your flu vaccine. And even if they're wrong, which sometimes they are, you can still getting a flu vaccine helps because your body recognizes maybe a branch of the flu strain, right? That branched off and became way more I just completely shut down. But maybe it branches off, like the alpha and the gamma and the beta strains of COVID-19, right? So like if you got the COVID vaccine, you could still fight off the Delta variant or whatever, right? So they're versatile; they could keep track, and that's all due to adaptive immunity. And there's a tolerance level, right? So you're lowering that tolerance level, which makes sense because if you have a whole bunch of cells in your body that will recognize that virus, it makes sense that it's going to run into that virus earlier, right? So you're not going to be able to, it's not going to be able to build itself up as much as it would be. Instead, your body's going to, it's going to build up a little bit. Your body's going to run into it and go, oh, hey, get out of here. And then it'll kick it back down, okay? So there's a tolerance level. This is a T lymphocyte. So remember, there's T lymphocytes, T and B cells. They are indistinguishable, but can be differentiated with surface receptors and also some histology stains. You can differentiate them too. All right, so cell-mediated immunity. So that's T lymphocytes. They don't recognize infection directly, so they don't stumble upon a COVID virus and go, "Hey, you're a COVID virus. I hate you. Let me perform hate crimes against you." No, that's not what happens. So there's other cells called antigen-presenting cells, which are infected body cells, right? So once the COVID-19 gets into the cell, it will proliferate, and then that cell becomes infected, and it puts out antigens, right? So your lymphocytes are going to see those antigens and they're going to go, oh crap, there's COVID in here, and it's going to start a response based off of that. Okay, so specificity utilizes major histocompatibility proteins or MHC proteins. There's MHC1 proteins which respond to CD8 markers on T cells, and there's MHC2 proteins which respond to CD4 markers on T cells. Okay, one proteins CD8, two proteins CD4, two different mechanisms. Okay, but pretty much the same thing. Got it? Got it. Let's talk about MHC1. So this is a complex. You're gonna have to know this whole complex and the thing, whatever that goes through it. The picture. Know the picture. All right. So there's CD8 markers on T cells. So this is a T cell. This is a CD8 marker. This is the complex, right? A protein complex. So it's building this protein complex. It's responding. And then it's creating FAS. Another protein. It's creating another protein, sorry, a FAS protein. And that is eliciting a response towards the virus. Like it's recognizing the virus, right? So the virus is entering, your body is letting out MHC class 1, right? It's creating a complex, and then that complex starts picking up the virus and creating antigens, okay? So antigen presenting cell with MHC2. So if, let's say, a bacteria is engulfed by a macrophage, and in case of a vacuole. So a macrophage is just kind of floating around. It sees a bacteria. It goes, hey, you don't belong here. I'm going to eat you. Yum, yum, yum. Okay. So it does that. And that happens by phagocytosis, right? So it's creating this like bubble around the bacteria. It's not just like pulling the bacteria in. It's creating a bubble, and then that bubble will break off and kind of float around inside the cell. It's putting it in jail inside the cell, okay? So lysosomes will fuse with that vacuole and start to digest that, okay? That's going to release proteins. So MHC2 proteins will respond to antigens from the digestive bacteria. So like little markers, right, that are released because you're breaking it down. It's almost like if you were to like if you eat a steak, right? You're breaking down the big proteins into amino acids. So you're breaking it down into little building blocks. Same thing here. You break down that bacteria into the building blocks. Your body recognizes those building blocks and then creates antigens based off of that. So those antigens are caused by pieces of bacteria fusing with MHC2, and then they present on the cell surface. Okay, so macrophages now will present these antigens, okay, and they'll respond to CD4 markers on T cells, okay? So T cells will eventually run into these and a response will be elicited, okay? So antigen processing and presentation, how does that process happen? Okay, so this is a macrophage, right? And it made a vesicle and it ate a bacteria and it said nom nom nom. Okay, so now you have MHC2 proteins that are floating around and reacting with the antigen from the pathogen, right? And then those link together and present antigens. So it's what's this word for it? It's sticking out a foot. There's a word for it. I can't remember what the word for it is, but it sticks out like a little thing, and it's wiggling it around, and then your T receptor cell will pick up on that, or your T receptor will pick up on that within the T cell, and that will pick it up. Okay. So the dendritic cell is now presenting antigens, which will activate T cells that bind with the MHC protein, right? So what you're doing now is you're activating that T cell, and the T cell is sounding the alarm. It's going, oh crap, there's something floating around here that's not good. Okay, let's go kill it. Got it? Okay, and this is the MHC1 proteins. So those do kind of similar things. Okay. T cell receptors. So if this is the transmembrane region, so this part right here, right? There's a constant region and a variable region, okay? and it's anchored into the transmembrane region. Okay, so there's something going on. There's something going on at a chemical level right here that it can't unlink, right? So this constant region is presenting a variable region, okay, and it can't unlink, so it's stuck. It's like you put I don't know, you put a key in the lock, and then you can't move the key, right? Because it's the wrong key. Okay, so those variable regions, um, okay, so if this is a antigenetic determinant, right, a protein, the variable regions of different T cells will respond to different areas of the protein, okay? So it's doing that. And that will elicit different responses, okay? So, pathogen presentation. This is okay, so if this is the dendritic part, right, of a cell, so antigen presenting cell, helper T cells will release cytokines that activate much of the adaptive and non-adaptive immune system during an infection. So these helper T cells will release something like a hormone almost, right? That your body will pick up on, and that will activate much of the immune system. So this T cell, right, responds to the antigen, and it becomes activated. Okay, so once it's activated, like this is what immunity is. Okay, so you don't fight it always by punching it in the face, right? So T cells, like these helper T cells, are going to fight it by releasing what are called cytokines, and cytokines are like toxic enzymes that are specifically toxic to mostly the antigen that you're trying to fight, not the antigen that you're trying to fight, the invader that you're trying to fight. So they'll release specific cytokines based off of, is it like a bacteria you're trying to kill or a virus you're trying to kill? Let's create a inhospitable environment for that, right? Okay, so that will react with infected cells and it will lyse them, okay? And these it will release things called granzymes and perforins. Okay, so those get released. If this is an infected cell, the T cell will recognize it, and then it will release the cytokines, which will respond and kill the cell. Okay, it ruptures the cell membranes. A lot of killing cells is just breaking the membrane up, right? It's a balloon. They pop the balloon. All right, so there's different types of T cells. So we have helper T cells. Those produce cytokines that stimulate the proliferation of other immune cell types. So these helper T cells are getting its friends together and they're going, hey, you guys got to join the attack against this infection, right? There's also cytotoxic T cells. So these are called killer T cells. And they are stimulated by infected cells, and helper T cells also recruit these to attack virus-infected body cells and cancer cells. Okay, so it's not just it's not just virus and bacterial infections, right? We're also fighting cancerous cells too. So you're picking up on an antigen that's being released because a macrophage has eaten a cancerous cell and recognized it as a foreign invader, right? So cancer, and that happens all the time. Cancer is just a cell that is proliferating way too much. Okay, so there's nothing like crazy special about cancer cells. There are specific physiological things that are happening within cancer cells, but they're not just they're just normal cells. They're just like you and me, but there's a lot of them, right? But there's certain flags that cancer cells release, that helps the body recognize those as, hey, there's something wrong with this one. It's a little weird in the head. Okay. So viruses and bacteria, and then cancer cells as well. Those are attacked by cytotoxic T cells. Okay. Suppressor T cells shut down the activity of T cells and B cells once the infection has been conquered by the secretion of suppression factors, right? So your body recognizes that it's killed pretty much everything, and then more T cells will come in here and they'll negatively inhibit, right, the T cell response. Okay, so it'll basically say, hey, there's way too much, and it'll slow down the response. Where else do we see this in the body? That's a question for the class. Where your body recognizes that there's too much of a response going on and it shuts it down. Yeah, negative feedback, endocrine system, right? Yeah. So it's all kind of clicking now, right? So you're getting your body reacts in a similar way. It's a different system, right? But if you remember how the negative feedback loop works, you can remember that like your immune system works the same way, but instead of hormones, we're talking about adaptive immunity, right? So it's shutting it down, not by releasing something that says stop, or not by releasing something that says, hey, bring it back in, but it's basically saying, hey, you don't need to do any more. It's done. It's dead. We can chill out a little bit. Okay. All right. So then there's also memory T cells. So those remain in circulation long after the infection's over to respond to future infections by the same pathogen. So it's preventing rebound, right? So there's memory T cells that are short term and they stick around for, a couple days, weeks, months afterwards. And then there's also long-term memory T cells, which prevent infection for longer periods of time, right? Like you don't get sick from the same thing that you did as a kid. You get sick from new things, but not the same thing that you did as a kid. These also help with rebound infections. So if you've ever wondered, like, why, if I get really sick, it might be a couple weeks or month before I get sick again, okay? That's because your immune system is operating at DEFCON 5 at that point, and it's killing everything, right? So mostly it's trying to prevent future infections by the same pathogen. So it's going, you're not going to come back, buddy. But for the most part, it also helps head off other infections, right? So the more T cells that are in circulation, the more you can recognize other infectious things that are happening, right? No click. What's this do? Let's click on this. Let's see what happens. Am I sharing my... Hang on. Let's see what this says.
And dogs, and I made them into a successful business.
There's no audio in case you were wondering. All right, so let's see. So cytotoxic T cell and a T cell receptor will respond to a class 1, right? This activates that T cell and it goes off and it fights the infection. This is a virus infected cell. It's going to link to it, right? Recognizing the antigen on that cell, right? It's going to bind to it, and then it's going to release cytokines into the area around it. That creates an inhospitable place, and then it will release perforin and enzymes, which will link together and create openings in the cell membrane, right? So we're lysing the cell membrane by opening it up, right? And then some of the granzymes will enter that opening, and that will speed up, right? So it's almost like opening up a hole and dropping a whole bunch of salt in it, okay? Making it worse. Cool. I like that. That was easy. Should have just figured that out. All right. T cell differentiation. All right. So the thymus. All right. So the thymus is an organ within the lymphatic system, if you believe in that. That its whole job is to mature T cells, right? So we call this process differentiation, and it happens within the thymus. Okay. So thymocytes from bone marrow will enter the cortex, right? So if this is, let's just say like this right here is the cortex, and if this is like the medulla of the thymus, right? So we're going from outside of the thymus to the inside of the thymus, okay? Oh, it's literally labeled, okay. So if this is happening in the cortex, so thymocytes, will create an MHC complex with epithelial cells in the thymus, right? And there's an immature thymocyte receptor, okay? That will create a CD8 receptor and a CD4 receptor. And so now this cell has an extra receptor on it, right? And then your antigen from the body cells will float through, right? These dendritic cells will float through the thymus, and they'll see those CD4 or CD8 receptors, or they won't. They'll bind to them, right? And then it will create a sorry, my dog started licking himself, and I just blanked again. So I need to loop it back in. All right. So they present antigens from other body cells, right? So this antigen was picked up from somewhere else in the body. This dendritic cell is floating through the thymus, and the thymocytes will bind with the antigens, and then they'll undergo apoptosis, which undergoes apoptosis. Hang on, I think this wording is weird. Let me read it again. Okay, gotcha. Yeah, so basically they'll pick either CD4 or CD8. They'll express that, and then they will mature into helper T cells, right, that are expressing the CD4 or CD8. Okay, so this one is expressing it. This one is negatively expressing the other one, right, and then positively expressing the 8. So it's either 4. See how 4 is positive here, and then 4 is negative here, or it's CD8, negative, positive, and then those will specify even more, okay? So they're becoming specific, right? Cell specificity. And they're differentiating into different types of cells. So these are both mature T cells, and they do different things, right? And that all happens in the medulla of the thymus, okay? And then they're released to the lymphatic system. So that is when they then float around the body and recognize, right, those proteins, okay? Respond to that and then activate. So these are just floating around in the body. They recognize and they activate, okay? So they mature in the thymus. Sorry, that was a little confusing for me too. That it's worded weirdly on the slide. I just want to make sure I told you this the right thing. This is the same kind of thing. Let me make sure there's not new information on this. All right, so activated T cell. This is basically all this is saying is that activated T cells will also continue to proliferate, right? They still undergo cell division, and so during that time, they will divide as activated T cells, right? And this happens in response to an infection. Okay, so they're activated. They stay immature, right? Until they are activated by an infection, and then they build up, right? Which is why if you look at like, let's say your blood cell, right? If you get a CBC, a complete blood count, your WBC should stay at a certain level, right? So we're counting the number of lymphocytes within your body in a WBC, okay? If you're undergoing an infection, those lymphocytes will proliferate exponentially, okay? So that's what's happening in this. The body is recognizing an infection, and it's proliferating lymphocytes. And so if you were to take blood from somebody that was undergoing this problem, their WBCs would be elevated. So if a normal one is under 10, if it's 6 to 8, these people's WBCs would be like, I don't know, 15, 20 to 25. And that's because of this right here, undergoing growth. Not growth, cell division. Okay, so adaptive immune responses, B lymphocytes and antibodies. So obviously it involves B lymphocytes. It's called humoral immunity, and it directly recognizes the antigen, okay? So sensitized B lymphocytes undergo clonal expansion. So these are mature B lymphocytes that are undergoing clonal expansion, which is this process, right? So cell division, okay? And they are directly recognizing the antigen, okay? So if this is an antigen that's being presented from like an infected cell, these B cells will link to the antigen at antigen binding sites. And this is just a protein that's embedded in the B cell membrane, and they will bind to the antigens, okay? So T cells, remember helper T cells, right? Helper T cells are like, hey buddies, come respond, right? The reason they do that, and the way that these B cells know that they're in the right place is that they will link to a T cell, okay? So this T cell, or sorry, this B cell is just floating around. It sees this antigen and it goes, hey, there's something going on. So it comes over to the infection site, right? And it links to the helper T cell with an MHC2 complex in CD4, right? And then that will activate the B cell, okay? So the T cell is releasing cytokines, and then the B cell is releasing cytokines, okay? Sorry, the B cell is not releasing cytokines. It's responding to the cytokines that are being released, okay? So this binding and these cytokines will activate the B cells. Cool. So those B cells will go on to link directly to the antigen on the bacteria, okay? And that will create a CD4 MHC complex with the helper T cell. And then these B cells, these memory B cells, will proliferate, right? So this is preventing post-infectious infection, I guess. Okay. And then they will also create plasma cells. So plasma cells are a type of memory B cell, and they're just different. Okay, and so these have the antigens floating around. These are the kicking the antigens out. So the antigen receptors. Okay. All right. Cell-mediated immunity. What is dendritic cells? Let's see what this does. 404 not found. Okay. That one doesn't work. All right, so helper T cell becomes activated by binding to an antigen presented by an APC via the MHC2. So antigen presenting cell, right, via the MHC2 receptor, causing it to release cytokines. Okay, so MHC2 receptor binds to the antigen and it releases cytokines. Okay, so this activates the humoral or the cell-mediated immune response. Okay, are we going to go through both? Maybe. So it's going to bind with the helper T cell, and then it's going to create clones, right? And then those B cell clones itself and creates a humoral immune response. Okay. Or the cytokines that activate the B cells and the T cells, those cytotoxic T cells will release cytotoxins, and then you'll have a cell-mediated immune response. Okay. What do antibody structures look like? So they're proteins, right? So they look really like that. If you were going to do a micrograph, they are typically a 4-chain structure of genetic antibody, of like a generic antibody. So they have like this generic region that's constant, and then they specify through this variable region based off of what's going on and what they're trying to bind to. Okay. So the reason they have this constant region is because you want to catch coronavirus, right? You want to catch the alpha, beta, the gamma variants, right? But when you run into the beta chain or the beta variant of SARS-CoV-2, you want to be able to recognize it, right? So there's a variable region that will specifically pick up that virus, okay? So this is kind of what antibodies look like. There's 5 different classes of antibodies, okay? They're called immunoglobulins, okay? So immune system, globulin, protein, okay? So immune system proteins, all right? What's important about this? I'm gonna say if you can memorize that there's 5 types, right? If you can recognize these pictures and say IgM pentamer, and IgG monomer, right? And then a secretory dimer. So a dimer is 2 proteins that are linked together. There's IgE monomers and IgD monomers, okay? So the IgE have a bigger constant region and the IgDs have a smaller constant region, okay? Heavy chains, I don't think you probably need to memorize what the heavy chains is. I wouldn't memorize the number of antigen binding sites so much as I would be able to recognize like these IgM pentamers are big, right? They have 10 binding sites. And then all the other up 2, except for the dimer because it's 2 proteins linked together, okay? Let's see what else about this. Probably be able to recognize that IgG monomers are the most common, right? Whether or not it crosses the placenta is important. So this most common one also crosses the placenta, and it gives innate immunity to a baby, right? So if these are floating around in a 35-year-old pregnant woman, all of that immunity that's building up over time, it's taken that 80% of that adaptive immunity and it's pushing it into the baby. So it's picking up antibodies, okay? Fixes complement, probably don't need to know that. FC binds to, just know which ones bind to something, right? And then know the functions, okay? So know where to find each of these. Stuff like this, where it's secreted into the mucus, tears, saliva, or colostrum. Like a good question from that would be, what if you're breastfeeding, right? What type of antibody is most likely going to be related through the colostrum? That would be like a good question to know. Okay. Allergy and parasitic activity. know, like this is probably important to know, like that it's responding to antibodies of allergies and parasites. Yeah. B cell response. Okay. So these B cells clone, right? So the clonal selection of B cells happens. And then during a primary B cell immune response, both antibodies secreting plasma cells and memory B cells are produced. Okay. So we have plasma cells that secrete antibodies. So all of these antibodies are secreted by plasma cells. That's their point. They're kicking out these antibodies so that those antibodies will link to infected cells. Okay. The memory cells lead to differentiation of more plasma cells and memory B cells during secondary responses. So if you have a primary response, like this is like I got sick the first time, right? The first couple days, all of this is happening. We're creating an immune memory, right? And then we've killed pretty much all of them, but we still see one kind of floating around, right? And that's going to cause a huge response, like a big rebound response and a secondary response. Okay. And this one will create all of this. Whereas the same one over here is only going to create a smaller response. Okay. So we're creating a much larger response on a secondary response. All right. Antibody defense. So they can either bind to a virus and neutralize them, right? So like this virus can't do anything now, right? But there's also little flags on the viruses. So the macrophage is going to see those flags and eat it, okay? All right, so they'll neutralize it and they won't be able to do anything. And then as they're floating out in space, not being able to do anything, you have a process called opsonization, where a pathogen tagged by antibodies is consumed by a macrophage. So the macrophage is going to see that pathogen, see the antibodies, and eat it all up. Nom, nom, nom. Okay? This will create a complement activation where antibodies that are attached to the surface of the pathogen will activate the complement system. Okay? And that complement cascade, like, remember what we had was innate immunity. Okay? So there's an innate immune response. So that also goes with this. So primary and secondary antibody responses. So if you have initial exposure here, remember you have that primary immune response. It's a lot smaller. It's a lot more balanced. And then say a week goes by, you fought it off, you're getting better. One of those little buggers is hanging around, and your body goes, "Oh hell no!" And then huge immune response, right? So you get this massive immune response. Okay. So you have humoral immunity. What we talked about is it can be active or passive. So active humoral immunity is naturally acquired. It's activated by contact with pathogens and infections, or it could be artificially acquired via vaccine, right? So vaccines work through humoral immunity, through active humoral immunity. Okay. You can also have passive humoral immunity, and that's naturally acquired. And so, like we said, antibodies that are passing from mother to fetus through placenta or as an infant in milk. So, as you're growing a baby, you're passing as much immunity as you can. As you're nursing a baby, you're passing in as much immunity as you can. And then that whole process happens over months and like years, right? It can also be artificially acquired by the injection of an immune serum. So there's vaccines and then there's immune serums, right? So like a hepatitis B immune serum, right? That's an example of one. So you just like won't get it, right? Okay. What else we got? Immune responses. All right, so the complement cascade. Did we already talk about the complement cascade? I feel like we already talked about it. We did. It's right there. Yeah, I'm not going to go over it again. These are the same slides. IgA immunity. Let me just go over this real quick. So just know that in nasal associated lymphoid tissue and Peyer's patches, so those areas of concentrated immune systems that are like close to your barrier defenses, right? They generate IgA immunity. Okay, so IgA. If you ever see, you'll see this with like serologies or blood tests and stuff. You'll see like IgA, IgG. This Ig, the big I, little g, stands for immunoglobulin, right? So immunoglobulin A, immunoglobulin G, whatever, right? And A and G, it's not as important as you know that this is just immunoglobulins, okay? So immune system, globulin proteins. So they're immune system protein A, immune system protein G, right? So both of those use M cells to transport antigens inside the body, and by both I mean Peyer's patches and lymphoid tissue in the nose. So that responses can be mounted. So basically, what's happening here is the antigens haven't entered the body yet, right? So if this is an epithelial lining, this is a lumen out here, okay? And your body is recognizing, you have M cells that are bringing that antigen in. Your body is recognizing it as, oh crap, we need to have an immune response because this thing that's trying to get in is bad. And it will create like a first line of defense right off the bat, okay? So it's almost like if this is the castle walls, right? And this is France, this is England, and France is trying to knock down the castle walls. They send out a spy and they go, it's the French. And then they run back in and they go, the French are here. And then they put archers up on the wall. Okay, that's exactly what's happening right here. All right. Or it's the nice of Sydney. Okay, immune system disorders. Let's talk about immune deficiency, hypersensitivity or allergies, autoimmune diseases, and graft rejections. Let's do immune deficiency, right? Okay, so everybody knows what AIDS is. Hopefully none of you have it. There's different types of immune deficiencies. Okay, so there's severe combined immune deficiency. There's acquired immune deficiency. SCID is genetic, I think, and AIDS is not genetic. I'm pretty sure. AIDS is definitely not genetic. Okay, so this is what's happening. So you have a virus, right? So this is the amount of virus. And then as the amount of virus exponentially increases in the blood, normally you would have a T cell count that also would respond. And then your T cells would keep the virus level down. This is called viral load, okay? So you would have a lot of T cells floating around, and that would keep your virus down, okay? Now, eventually, that'll fall off a little bit over the amount of years, and then the virus will increase, okay? So this is HIV infection over here. This is AIDS. You can kind of think of it that way, okay? So the antibody response is, it's not in charge, right? It's controlling it, but it's not in charge. Kind of like a vaccine, you're not curing it, you're just controlling it. And so eventually that control will back off and then the viruses will kind of take over, okay? So that'll progress towards the disease known as AIDS. HIV is the virus that causes this. AIDS is the disease form, okay? So you can have HIV infection but not have AIDS. As long as your T cells are keeping up and you're keeping your viral load down, you will not develop AIDS, okay? There's medicine that can help your T cell count stay high so that your viral load will be lower, okay? there's a certain level here, and I don't know, this isn't labeled concentration, but like there's a certain level right here that this the viral load could be undetectable. Okay, in everybody with a normal immune system and not an HIV, you have an undetectable viral load of HIV. So you probably have some HIV floating around in there, but your T cells are killing it so fast that it's undetectable. Okay, everybody does. Well, viruses are everywhere. Okay, but if you are infected, like you stick yourself with an HIV needle, and then you inject a whole bunch of HIV positive blood into that, that will overcome, right? And then your T cells will be working too hard to keep track of it, and eventually that viruses will kind of hit that threshold and your viral load becomes detectable, right? So you have AIDS at that point. You don't just have HIV positive. Okay? Fun fact, your boy here has been stuck with an HIV needle before. And that was not fun. Serologies came back negative though, so that was great. And I don't have AIDS, which is so good for me. I got stuck on my birthday actually. Worst birthday ever. And I also took a whole bunch of medication that cost $20,000. So that was super fun for me. Don't tell anybody that's a HIPAA violation. I'm just kidding. You guys aren't healthcare workers yet. All right. So, oh, and the other thing about HIV is like this is pretty controllable. Like you can control an HIV infection, which is why it's really hard to get AIDS and a positive HIV if you are stuck by a needle, right? Like you've really got to try hard. Sexual transmission is going to be the most common way you develop it, because obviously, like it's it could be like a repeated thing that you're being like constantly exposed to. But HIV is pretty weak sauce when it comes to viruses. We test for 3 different things at my work that I got stuck at. Like we have a rapid test, HIV, Hep C, and Hep B. And when the HIV was positive and not the Hep B, I was like, yes, I'm not gonna get Hep B because Hep B has like a 50% transmission rate with needle sticks. HIV has less than 1% with needle sticks. So it's way harder to get HIV than Hep B. So if you're gonna stick yourself with the right blood. Okay. All right. So immune hypersensitivity. So these are people with like overactive immune systems. Okay. I'm not going to go through like all of this. Just kind of know that it can either be an acute or type 1 hypersensitivity. Sorry. And this is B cell mediated, right? And then this one's also B cell mediated and also B cell mediated. And then type 4 is exclusively T cells, okay? So just T cells right here, no B cells, okay? And no complex happening, okay? It can either be acute, which is type 1, so like an immediate response, right? Like a localized anaphylaxis, people who get stung by a bee or have peanut allergies or something like that. It can be subacute, so caused not by like not caused by like a bee sting that can happen like immediate, but like if you inject the wrong blood into somebody, like if you get a blood transfusion with, if they're A negative and you give them B positive blood, then that blood's going to kind of coagulate and create like an issue. And that's a slow process. It's not like an immediate process. So, and those foreign blood cells will be destroyed by the complement and antibodies during transfusion. So like that happens slowly, right? Same thing with erythroblastosis fetalis. So like the fetus doesn't have the same blood type as the mother. The mother recognizes the fetus as a foreign invader and it kills it. Okay. Then you have type 3, which is delayed. So this is still like kind of subacute, right? Like this is happening like not fast, but like not slow. This is people with like long-term immune problems. Okay, so like rheumatoid arthritis, so your body is recognizing the cartilage as an invader and creating an immune response and attacking your joints, right? Or lupus, or like one of the other like autoimmune diseases. Okay. This one, type 4, is cell mediated. So these are going to be like, they can be acute. They're usually like long-term disease mediated effects. So like diabetes type 1, your body recognizes glucagon as an invader. You don't store it, right? So you need to insulin. So you need to inject insulin because it attacks the pancreas cells. So you need to inject insulin because your pancreas can't keep up. Multiple sclerosis. So your body's recognizing the neural cells, your skeletal neurons as invaders, and it's attacking the myelin sheath of them. And then rheumatoid arthritis as well can be a type 4 response. All right, so I kind of went through most of those. Is this one specifically pointed out? What's this, lupus? Rheumatoid arthritis, probably. Yeah, rheumatoid arthritis. So you can see right here that immune response is attacking the joints, right? And it's causing arthritis. So arthritis is not the immune response. Arthritis is a symptom, okay, of rheumatoid immune response. Okay, same thing with lupus. It's an immune response that's attacking like different body systems. Okay, so this one is lupus. So it's the joints can be attacked. You get muscle aches because the muscles are being attacked. You get mouth and nose ulcers because the mucous membranes are being attacked. So your face, you get butterfly rash. Your body's like creating an immune response. You're flushing. You have pericardial inflammation. Your fingers and toes will get poor circulation because your body's shunting the circulation to other areas that it's attacking. So not great. This is like lupus attack, right? And people could live with lupus, but it might like flare up at certain points, so it gets worse sometimes. Newborn hemolytic disease, so erythroblastosis fetalis. All right, so we talked a little bit about blood typing, and I lied and I didn't give you the videos on blood typing. I promise I will. Here's what you need to know for this specific section, okay? You can have, if you have a mother, say, who's A negative, and then that person has sex with a male who is B positive, you can create, remember Punnett squares, you can create a fetus that is that has the positive Rh factor in a maternal blood that's negative. Okay, so if this is the placenta right here, right? Let's zoom in on this section right here. So this we have within the placenta, it's an interconnection point, right? It's not just the mother giving arteries and veins to the fetus. It's both of them growing in the same direction, and they meet up in the placenta. Okay, so you have infant blood right here, which is positive Rh factor. So if this is B positive blood, right, and then you have maternal blood, which is A negative, right? Your maternal B cells will be activated because of the Rh antigen that's positive in the erythrocytes of the infant blood, right? So they'll leak into the mother's blood, and your B cells will become activated, and they'll start attacking those blood cells, and it'll create an immune response, right? So once that happens, remember we have memory, we have plasma cells that are going to be like, hey, this was an infection. I'm going to create plasma cells and release antibodies, right? So those Rh antibodies, they will titer in the mother's blood. So they'll be present in the mother's blood and they're floating around and they will eventually cross the embryonic chorion, right? Because they're small, they're just proteins, they can pass through between cells, right? And they'll start attacking the infant's blood within the infant's circulatory system, right? This is the infant circulatory system. So you're getting venous return of antibodies attacking blood cells. So you're returning blood cells that are under attack into the fetus, right? When that happens, you're gonna create even more antibodies in the maternal blood. Okay, this is the second exposure. So remember, just like we had with the plasma cells, you have that first exposure, your body fights off the thing, and then there's a second exposure that just it's an exponential response. So the mother will pick up that it's fighting that fight again, and then it'll just send a whole bunch of immune cells and attack the fetus. Okay. So you can prevent this if you want. There is a medication called RhoGAM. So you have to give anti-Rh antibodies during the first pregnancy to destroy the positive fetal red blood cells from entering your system. So that'll basically like protect. It'll bolster this, and when they slip out, the RhoGAM will be like, no, don't do that, and then it'll kill it before the plasma B cells will be able to see it. Okay, so the infant can survive because you're not creating that second exposure response. Okay, so you have to catch that early. I don't remember exactly how many weeks you have to catch that, but let's see if it says it down here. It doesn't. You have to pick up on that early. Okay, so yeah, it's an immune response that's mediated by B cells, by plasma cells. Okay. Kaposi sarcoma lesions. So sarcoma means, I'm going to Google it so I can give you exactly. Sarcoma definition. This is anatomy, so we're going to talk Latin for a second. Sarcoma. Just hold it a few minutes here. So SAR is connective, and then OMA is tumor, right? So it's a cancer of the connective tissue. Okay, so connective tissue is like a really broad term, and it's not just like weird like fibrinogens floating around. It can include like bones, skin, muscles, and stuff like that. So this is an example of Kaposi sarcoma. So let's do our favorite game, which is Show Us That White Man. For the ones here. Moritz Kaposi. Here we go. Look at this goober. Okay, right there. Got something named after him. Right there. Cool dude. All right, so Kaposi sarcoma lesions. So it shows up. It shows up because in these lesions because there's connective tissue in the thing. Okay, so it's an immune response to the connective tissue that creates cancer. Okay. All right. Graft rejection. Who wants to learn about what I do every day? All right. So we have grafts. And By graft, I mean like transplant. You know why all the white men? I don't know. Ask white men. You rule around for a couple hundred years, and you just start naming crap after yourself. So graft rejection. So let's. No. All right. So there's different types of grafts. Okay. So you have autografts, isografts, which you don't really hear about those very much. Allografts and xenografts. Okay. Let me look at this and see if it's breaking down. No, it's not. Okay. So I'm gonna keep it on here for a second. Okay. So autograft. Autograft is my own body. Okay. So I'm taking a graft from myself and I'm transplanting it to myself. So if I get a burn, you're going to take a dermatome like strip, right? You pull the dermis layer off, and you can create your own skin grafts, right? So if I burn my chest, they can create strips off my legs and put those on. Those don't get rejected. Why do those not get rejected? Participation. Same cells. It's your cells, right? Your body doesn't recognize it as a foreign invader. Okay, it recognizes that you have taken something and put it on top of it, so you're still going to get like inflammation and stuff, but you're not going to get a true rejection of the graft, right? Because it's your own cells. There's nothing foreign about it, and your body is not going to go, okay, like I don't know where these things came from. Let's kick them out. Okay. All right. So that's autografts. So that's one option. And that's usually within like tissue grafts. Okay. You can't, it's kind of hard to transplant a kidney yourself. Isografts. I don't know how many good examples of isograft. Let's see if I can. Yeah, of course I Googled it and it's all straight up allografts. So I'm not even going to talk about isografts. So allografts, let's talk about allografts. Allografts are grafts that are transplanted from somebody else, okay? So organ transplantation comes from somebody else. Tissue grafts come from somebody else. So you run this risk of rejection. Now, I'm going to give you the difference. All right, in organ transplantation, that organ has to function, right? We have to keep that organ alive, functioning as if it's still in the original person, okay? So in order to protect it, we go through an entire system of matching blood typing. There's like 10 different things you have to match. So it's not just like take a heart out and put it in somebody else. And it's not just take a heart out of an A positive person, put it in an A positive person. It's even more complex than that. There's like 15 things that have to match up in order for that person to be a suitable recipient of this graft. So that process is not just one surgeon calling another surgeon going, hey, I've got a heart. Do you want this heart? Yes, let's check the UNOS list and see if they're at the top of the list. Oh, you are at the top of the list. Do you want this? Yes. All right, here you go. It's not that. There's about 40 people that are involved in an organ transplantation surgery, okay? You've got people who are getting authorization and talking to families. You've got critical care workers. You've got people that are keeping those donors alive to become an organ donor. You have to die in like really specific scenarios where you didn't damage that organ and you didn't cause enough damage while you're dying, but you're still not going to ever recover from it. Okay. Less than 1% of people will ever become an organ donor. Okay. Because you have to die in a very specific way. Now, there's other people that their job is to place those organs. So they run all those 15, 20 tests, right? And then we put it into an algorithm. So everybody knows I'm at the top of the transplant list, right? Like that's the big thing. There is not one list. So let me explain to you the organ donation system in America, because this is my favorite thing, and I have 6 more minutes. You have to listen to me. Okay, so There are 13 regional lists throughout the entire country. Those lists are managed by local federally designated organ procurement organizations. So some company somewhere has a designated region and they have to maintain the donors on that list as recipients. If they're brain dead and state of availability, it's easy to become a donor. Yes, but it depends, and we're going to keep going on that. All right. So somebody somewhere has to decide like that region, right? So like for instance, I work for a company called LifeLink. We are the federally designated OPO for all of Georgia and 2 counties in South Carolina. Okay. There's 56 organ procurement organizations in the entire country. So there's 56 OPOs. All right. So there's 56 companies that have 40 people per donor that are all communicating all at once. So we do go through UNOS, kind of. Sometimes we pick up the phone. Now, there's other people that have to figure out the logistics of that. I need to call this surgeon and make sure that they don't have 50 patients tomorrow, that they can't come recover this and whatever, right? So we have to match all of those other immune trigger points, right? So IgGs and IgAs and IgBs and all those. So there's like a bunch of them. So you catch the big ones, there's like 10 big ones, and then you match as many of the small ones as you possibly can. So it's not just one list. It's a list that has an algorithm within it that's 13. It's regional, right? Because you can't get a heart from Boston to San Francisco. You need to transplant people within Boston. That service area, you need to get transplantations within that service area, okay? So you have this big list, there's a whole bunch of criteria, and you're picking the top couple people of that list and saying, I think they're most suitable for this person. That person could be number 5 on the list, okay? They're the 5th most critical person in that entire area, in that service area, but they're the best match for this donor. So they're gonna get it, okay? Sometimes you go 50 people down the list before you find a suitable match. So just because you're at the top of the list doesn't mean that you're the next person to get an organ. It's so complicated, and it's beautiful. I love this system. It's terribly overcomplicated, and there's a lot of flaws, but it's an awesome way to do medicine. Now, rich people get transplants faster than everybody else. Why? Because they have access to a private plane. So at any point, they can get on all 13 lists and be the most suitable person on 13 different lists and get a phone call and say, hey, you gotta be at the hospital in 2 hours. Yep, it is sad, it's horrible. And then they will jump on a private plane, fly to that area, and pick up an organ. Yes, it's extremely unfair, but we're never gonna do anything about it because we live in a country that runs on money. Okay, so that's organ system. It's super complicated and it's really cool. And it's like there's like way more into it than ever. Okay, so that's allografts. You also have tissue grafts, which is what I do, which is super fun. The tissue grafts that we produce, those go through certain processing measures. Okay, so you're decellularizing, so you're killing off all the local cells of the donor, and you're creating a tissue product that can be then transplanted into a recipient. Now, the benefit of being able to decellularize, because you're only using certain parts of that tissue graft. So if you take a bone graft, right, and you decellularize it, you're only left with a calcium scaffolding system. So your body isn't going to recognize that as a foreign invader, right? Which is so cool. So you can take that piece of bone from a tissue donor, decellularize it, irradiate it, kill all the living cells in it, and then plant it into a recipient where they will then, because we learned about bones, you have osteoclasts and osteoblasts, the recipient's own bone cells will start breaking down that tissue graft and building it back up in place. Fun fact, every 7 years, your whole skeleton replaces itself. So if you become a tissue donor and you take a bone graft from a donor and you put it in a recipient, or if you become a tissue recipient and you take a bone graft from a donor, after 7 years, it's not even donor bone. It's native recipient bone because your body has recycled it. and turn it into its own bone, which is super cool. So, is there graft rejection in allograft tissue grafts? The answer is no. We're out of time. So, there has never been a documented instance of graft rejection in an allograft because of an immune response, like there would be in organ transplantation. Xenograft is from a pig. So same thing as allograft. You can take heart valves from pigs, you decellularize them, they go through this whole process, and then you implant them into humans, which is super cool too. But it's killing my industry. So I'm not going to talk about it. Any questions? That's immunity. It's pretty fun. That's all I got for you. See you in lab. Bring your questions. How about this? Bring your questions to lab. And it's what? Did you say at the end? Oh, it's pig graft. Xenografts come from other stuff. So like pigs, cow valves, bovine valves, stuff like that. You recommend bone graft in dentistry? Yeah. It helps if you need one. Okay, bye. See y'all in lab.